This is lesson 2 of Unit 5 for Algebra 1A. We're talking about linear functions. In this lesson, we're looking at slope. I am going to go quickly through this content so I don't use too much of your data. So make sure to pause if you have any questions, if you're getting stuck, or if you just need more time to write things down. I do plan to upload a longer version with more details. In this lesson, you're going to calculate the slope of a function from a table. We're also going to calculate the slope from a line, and we want to compare the slope of two lines. Key terms for us here, slope and rate of change. Both of these are the same thing. Slope is specifically used when we're talking about the steepness of a line, so really we use that when we're talking about a graph. Rate of change is the same thing as a slope. We would use it when we're talking about a table more often. Slope, we would say that is the rise over the run. Rate of change is the change in y over the change in x. So when we say over, that's talking about it as a fraction. So we're going to put the change in y on top of the change in x. And rise really just is the change in the y, but as we see it on a graph. For all of these examples, we are looking at linear functions, so we see that they have that constant rate of change. This is what we had done in the first lesson. If we find the slope from this table, we're going to start by making sure that it's linear. We see that the y goes down by 3, and it does this each time. So 6 to 3, it goes down by 3. 3 to 0 is decreasing by 3. You can always check this with a calculator by subtracting these two numbers. 3 minus 6 gets you negative 3. On the x side, we start off with some negative numbers. It may be easier to start with the positives. This is going up by 1. This is going up by 1. You can always check this by adding negative 2 plus 1. You can see if it gets the same answer, or you could subtract negative 1 minus negative 2 and see what you get. In either case, we see that the change in y is negative 3. That goes on top. The change in x is 1. That goes on bottom. We can leave it like this, or because it's a fraction, we can divide that. Negative 3 divided by 1 gets you negative 3. Since that number is a whole number, we would go ahead and do that. Let's find the slope for number 2. Here we see that the x's are going up by 2, and we see that the y is going up by 1. So our slope puts the change in y on top first over the change in x. To make sure we always put the change in y on top. If we look at that fraction, if we look at 1 over 2, if we divide that, we get a decimal. So we're going to go ahead and leave it as a fraction. We'll talk more about that as we begin to make graphs. Try number 3 on your own. Find that slope. The next examples are going to be from graphs. So we said in the key terms, slope is described as rise over run. We're still looking at the change in y, but because the y-axis moves up and down, this is our y-axis right here, the change in y tells us how much that graph goes up and down. We need to use pretty points to find our slope here. So pretty points are just points that are at the corner of a box. Right here in the middle, we see a pretty point right here. It is at the corner of a box. It has 2 lines going through it. All we mean by pretty is that it has a whole number coordinate. If we look to the left, we see it cross one line. We see it cross one line. Here it crosses with 2 lines. So again, we have a pretty point. The coordinates there are whole numbers, negative 1 and 3. If we look down to the right, we see another pretty point right here. Now that we've found our pretty points, we can go ahead and find the slope. So we want to find the rise over the run. If we look at any 2 points on this graph, let's say I look here and here, I can go over 1 and down 3 to get there. Doesn't matter if I go on the top of the line or below the line. So this goes right 1 and then down 3. Because we're going down, we're going to make that a negative. The slope here is the rise over the run, so it's -3 over 1. Just like above, we can divide that to get -3. It doesn't matter which 2 points you pick. We'll look more at that in number 2. Here we have a lot of pretty points we can find. There's one here in the middle. To the right, there's 2 pretty points. Again, we see that it's the corner of a box or it touches 2 lines. And on the left side. For the first one, I find the rise over the run, like my formula tells me. I typically just go ahead and draw a little triangle. So if I start with these points here on the right, I would rise 1 and run 2. We count the entire box. That would give me a slope of 1 over 2. But you could also pick any set of boxes, or any pair of points. Let's say I picked this point and that point. I would have that same right triangle, again, following the lines on the graph. This time my rise would be 2 and my run would be 4. These are going to be equivalent. I can divide the top and the bottom by 2. 2 divided by 2 gets me 1. 4 divided by 2 gets me 2. This is simplifying a fraction. I do expect you to simplify fractions if possible. You can always pick the 2 points that are closest together and have a simplified slope. Try number 3 on your own. Next, we're going to compare slopes. A bigger slope has a faster rate of change, and that makes the graph look steeper. It's going to go up faster. It's also worth noting, a negative slope goes down and to the right. We saw that here. This slope was negative, just like the table above it. So we're going to find the slope for these tables and graphs, and we're going to compare them. And we're going to say which one is bigger. For table A, we find that slope with the whiskers. This goes up by 2 and up by 3. Again, we want to make sure that the y goes on top, so our slope for the table is 3 over 2. Since we divide that and we get a decimal, we get 1.5, we're going to leave it as a fraction. Now if we look at the graph, we start by finding our pretty points. As soon as we have any 2 pretty points, I would connect the closest 2 with a triangle. We see that the rise is 2 and the run is 1, giving us a slope of 2 over 1. Which of those slopes is bigger? Well, if we divide the top by the bottom, we get 1.5 over here, and we get 2 over here. So graph B has the bigger slope. Again, we get that number by dividing those fractions, the 1.5 and the 2. How about you all try, oh, my on-screen keyboard's popping up. How about you all try number 2 on your own? Remember, a steeper line has a bigger slope. Applications, people use slope many times in daily life. Slope often relates to time and money. We're going to complete these tables for the following scenarios. Remember that the the independent variable is x. These are the same thing. Number 1, you earn $9 per hour at your job. First thing I'm going to figure out is our variables. Well, I hear $9 per hour. Dollars and hours are both measurements of real-world quantities, and they have numbers with them. Which one is your input and which one is your output? We've got hours and money. When you go to your job, do you put in money to get hours back, to get time from your job? No, it's the other way around. You put your time in at your job. Hours would be your input or your independent variable, and your dependent variable, your output, would be money. We could also say that the amount of money you earn depends on how many hours you work. It's worth remembering that the independent variable is x, if we're making a table, X goes on top, so we're going to put our variables here, hours and money. If you work 0 hours, how much money would you make? Nothing. If you work 1 hour, you'd earn $9. If you work, finally, it goes away. If you work 2 hours, you get $18. If you work $3, 3 hours, you get $27. The word per tells us the slope when we read word problems. So we can already see that the slope is $9 over 1 hour. We can see that from the table here. We can see that the money goes up by 9, that's like our y, while the hours goes up by 1. This relationship is also proportional. We can see that if we use that slope and we take our input and we multiply it by 9, we get the output. Let's do one more example before you attempt the rest on your own. The teacher brings 2 pencils for every student. Well, we're measuring pencils. There's one of our variables. What else are we measuring? We'd measure how many students there are. When we think about the input and the output, which one depends on which? Would I, as a teacher, make my class size, would I make the number of students depend on how many pencils I have available? Well, no, I don't get that choice. I am told how many students I have, that's my input, and as an output, I buy an appropriate number of pencils. So pencils depends on how many students I have. Input is students, because if I use this function machine and I tell it how many students I have, it's going to tell me how many pencils to get. We're going to put students on top, pencils on bottom. We're going to complete this table. If I have 0 students, I don't need any pencils. If I've got 1 student, they're going to need 2 pencils. 2 students would each need 2 pencils, so that would be 4 pencils total. 3 students would mean I need 6 pencils. Again, we see that slope with the word every, just like the word per. The slope is going to be 2 pencils per 1 student. We see that from our table with the rate of change. The pencils changes by 2, and the students changes by 1. Try those last 2 examples at the bottom of the page on your own. Think carefully about your variables and complete the table. From here, there'll be a quiz on the website.